One of the best things about STEP is that many of the questions will make use of ideas from undergraduate level mathematics. These ideas will often be naturally at the forefront of the minds of the examiners, and can be nicely adapted in a way that makes them accessible to sixth form students. One such idea is the exponential of a matrix, which sounds quite counterintuitive, but is a very important concept, for instance in the study of objects called Lie groups and Lie algebras. In this video, we're going to work through part of a problem from Step 3, 1998, making use of this concept. Now that matrices have returned to the STEP syllabus, it's likely that such a question could also be set in the future. The main subtle trick that we're going to have to use to solve this problem is also really the only main subtle trick that could be deployed in such a question. So at the beginning of the question, we're given the definition of the exponential of a matrix. Although the STEP question setters can and will introduce new ideas, for example, from undergraduate level mathematics, they cannot assume you've met these ideas before, and so they'll always need to give you any definitions that you're going to require. Nonetheless, experience with these sorts of ideas from past papers can obviously be really helpful, because if they do introduce this question again in a future paper, it's going to be a significant advantage to have prior experience working with this notion. So we have this notion of an exponential of a matrix, and it makes perfect sense when you remember the definition in terms of a Maclaurin series for the exponential of a numerical variable. So we have exactly the same expression where it's just x, some numerical variable x. So what we've done is we've taken this formula, which does make sense for a matrix because you can take powers of a matrix, and we've simply stuck a matrix value instead of a numerical value. Of course, it doesn't make sense outright to talk about e to the a in terms of, the ordinary laws of operations upon matrices, but powers are fine, and so we use this as a route to generalizing the notion of exponentiation. So it makes perfect sense. We're given a matrix M. The first thing we need to do is to verify that m is minus the identity. So that, m squared rather, is minus the identity. So that's going to be a very straightforward computation. Because it is very straightforward, and because it is a show that, I'm going to include slightly more steps than perhaps I otherwise would if I was squaring the matrix. So I'm not going to go straight to writing minus I. I'm first of all going to write it with the minuses as they naturally arise when you do the matrix multiplication. Then I'll pull the minus out, and then I will observe that that matrix that remains is the identity. So I'm not suggesting that if you, for example, skipped this step, you would necessarily lose a mark, but it's best to be safe in a show that, just to be completely clear that we're not bluffing. Now, they're obviously not really interested in step, especially step 3, in assessing whether we're capable of performing matrix multiplication. This is a really easy procedure. This is obviously being set up for use later in the problem. Considering the fact that an exponential involving m is going to involve lots of powers of m, the fact that m squared is minus I is obviously going to be really helpful in simplifying the subsequent powers. Because every time I find myself with 2 powers of m, I can just bunch them together into a minus I. I'll never get powers of m higher than 1 actually surviving in the expressions. So this suggests that in this series, there's going to be a dramatic simplification. So although it's the exponential of theta m we're after, powers of theta will just pull out of the matrix. That's not going to be a complication at all. Let's quickly think about what happens with the various powers of theta, powers of m rather. Given that we are going to add up infinitely many of them, presumably there will be a really simple pattern. So if we just consider, as a sort of preparatory exercise to get ready to take the exponential, the powers of m. So m to the 0 is the identity. M to the 1 is m. M squared, we just proved, is minus the identity. That means m cubed, if I just multiply that by 1 more m, is going to be minus m, because I times m is m, and the minus, or I times m is minus m rather, or I times m is m, but you've got the minus out front already. And then finally, if I multiply through by another m, I've now got an m squared again, which becomes a minus I. That cancels this minus, and I'm back to I. So clearly it's just going to loop, because now I'm going to get an m again, then two of them's going to make a minus I, and so on. So I've clearly got just a period 4 pattern, and I'm only going to get i's and m's. So now what happens if I put the thetas in? Well, if I'm looking at powers of theta, it doesn't really change anything. It just means that the thetas sit out front. So theta to the 0 is 0. That one doesn't change. Theta to the 1 is theta, so I get a theta there. Theta squared obviously pulls out, and I get that. Theta cubed, likewise, I get that. Theta 4, likewise, I get that. So it's obvious that I'm going to get, as each subsequent term in the expression for the exponential, more and more powers of theta. But the matrix part is always just going to be an I or an M. The obvious thing to do is therefore to collect together the bit with an I, collect together the bit with an M, and see if we can simplify either. So in the exponential of theta m, which is, given in the question, sigma r equals 0 to infinity, 1 over r factorial, theta m to the r. Well, if I first of all collect the I bits, so I've got one lot of I, minus theta squared over 2 factorial. So we have to put the factorial in, because of course what we've written here is just the power of the matrix bit, but in the definition there is also separately a division by a factorial. Then the next one I get is a plus with a theta to the 4. And just to show the reader that we really have spotted the pattern and we're not just bluffing, we might as well go one term further. So I'm next going to get an I when I have 2 more m's to make another minus I. So that's going to be the 6th term, and it's going to come with a minus because 2 more m's will negate that I, because m squared is minus I. So we get that. So that's the I bit of my answer. And then the m bit is just as simple. First of all, I've got just the first term is theta m, so I get theta of them. The next one is a minus theta cubed there, which now comes with a 3 factorial. And then obviously, for example, the next one is going to be the one further than here. When I have one more m, that's going to be the 5 term, and it's coming with a plus. And again, the pattern will continue in the obvious way. Now, when in step we encounter an infinite series involving powers and factorials, usually the trick is going to be to spot that it's secretly the Maclaurin series of somebody. On step 3 in particular, you really need to memorize all the Maclaurin series given in the standard, say, A-level mathematics, further mathematics formula booklet. In particular, if you've memorized such formulae, you should immediately recognize that the coefficient of the I piece is just cos, and the coefficient of the m piece is just sine. So now there's no more infinite series, we've just got 2 things added together, and we can simply go in and put back in the expressions for I and m. So I, of course, is 1, 0, 0, 1, and m, we'll recall if we look back, is 0, minus 1, 1, 0. So multiplying in the sine and the cosine, adding these things up, what do we get? It's cos, sine, sine, cos with a minus on this term. So the last thing they ask us to do, other than computing this exponential, is explaining the geometrical significance. Well, if we've revised matrices at all, we should recognize immediately that this is a rotation anti-clockwise by theta about the origin. So this is actually something that's deeply connected to the idea I mentioned earlier of Lie algebras. What's really going on is the matrix we called M is secretly associated to infinitesimally small rotations by an infinitesimally small amount. And then the process of exponentiating is turning it in to a rotation which is no longer infinitesimal, but which acts with a finite angle of theta. Understanding this is way beyond the scope of STEP, but it's the sort of theory that you can look forward to at an undergraduate level. In general, we wouldn't advise spending too much time on older step papers, as the style has evolved over the years. But there are some really instructive highlights, and we'll be covering some more examples on the channel in the coming weeks. So do remember to subscribe. If you'd like to learn more about our intensive step preparation program and other support we offer at Vantage, also remember to visit our website. Thank you very much for watching.